All right, so let's go and get into identifying the phases in this phase diagram. This phase, this plus this plus liquid, liquid plus this phase plus liquid here. In this little section, it's going to be this plus liquid. Here, it's going to be this plus this. Here, it's going to be this plus this. Here, it's going to be this plus liquid. Here, it'll be liquid plus this phase right here. This will be this plus this right here. This will be this plus alpha. This will be this plus liquid here. Let's move over. This will be, and this will be alpha plus solid here. This will be BCC plus liquid right here. Here, this is going to be DHP plus liquid right here. And then this will be also basically DHP plus BCC. Again, I expect you to write it out more comprehensively than that, but we're just getting through these problems. All right, let's do congruent melting points. Here, 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 and here. Those are our congruent melting points. What about our invariant points? Let's go ahead. This is going to be eutectic, liquid to two-phase solid region. This will be a peritectic, so basically solid plus liquid to another solid. This will also be a peritectic. This will be a eutectic. Let's see, what else do we got here? This will be a eutectic. This is actually going to be a eutectoid because it's BCC to, or actually, excuse me, that is not true. Let's rewrite that. So this is actually going to be actually a very unique phase here. So this will be, actually this is a very tricky invariant point because it's not really an invariant point. Well, it is an invariant point in terms of there's three phases because it's BCC, liquid, but it's actually this right here. Sorry, excuse me. This will be BCC plus DHP. This will be an invariant point, but it's not really an invariant point, so I'm not going to mark that off, or not the ones that we've been talking about so far. But this is eutectic. This is a peritectic, solid to liquid to new phase solid region here. And that's pretty much it for our invariant points. Excellent. So we're looking at a composition of 0.55 at 950. So at 950, let's say we're right here. We're at 0.55. Excellent. We're in a two-phase region of what? Let's call this beta. So we're in our composition of beta is just going to be 0.5 here. Our composition of liquid is going to be equal to approximately, let's just call that 0.75. Our composition that we're interested in, our C naught, is going to be equal to 0.55. So my composition, or my fraction that's in the liquid phase is going to be, again, we run opposite, right? So it's going to be 0.55 minus 0.5 over 0.75 minus 0.5. And my fraction that's in the beta phase will be, again, run opposite. So it's going to be 0.75 minus 0.55 over 0.75 minus 0.5. So this is a 5.5. There we go. So makes sense because we're closer to that beta phase, so it should be beta. And I'm just doing beta for short term or shorthand to do this AGPR. Excellent. What are the phases? What are the components in the system? And name them explicitly. Ooh, excellent. So the components are AG and PR. So our degrees of freedom plus P is equal to C plus 1. So our components are 2. Our phases are 2. So our degrees of freedom is equal to 1. So we can only change temperature or composition before we that we can kind of move through here. So did that. What is the composition and fraction of each material? Did that. Relate the chemical potential of each phase in this region. If we're in a two-phase region, the chemical potential of liquid must be equal to chemical potential of beta. Excellent. And then we are degrees of freedom. Beautiful. Draw the free energy curves at 1250. So at 1250, let's say here, we're going to hit here, here, and that's it. So we are looking at a scenario that looks a little bit like this. So if I'm going to draw my free energy curves here. So I'm going to say at this crossover point here, we're pure liquid. Then from here to here, we're going to call this basically solid 1. So now I'm liquid plus solid 1. And then from here to here, I'm also going to be, let's just draw that. I'm drawing it exaggerated. That's also going to be liquid plus solid 1. And then after that, so that's in here. And after that, this is all liquid. So I'm going to change my color. So my liquid is going to be blue. So when I'm in a two-phase region, actually, let's go ahead. I need to have, basically, I need to have a common tangent basically here. And then a common tangent just here in this two-phase region. So I'm going to draw my liquid. Liquid is lower, so it touches here. It kind of escapes and touches again, and then is just low. And my solid, which is going to be this S1, it's higher, but now it touches this two-phase region here, touches here, and then it just escapes. There it is. That's essentially what it would look like for our free energy curve. Not too bad. Remember, when we have a common tangent, it means that our chemical potentials must be equal because our chemical potential is equal to, or roughly equal to dG. Actually, this is true, and it's roughly equal to dG mole fraction. Fantastic. All right. We'll see you in the next one. Thanks. Bye.